Hello, this video is for Stat 310, Handout number 10, Part B, and includes pages 11 through 18. All right, let's go ahead and get started. This data set is going to use the Lions Males Only data set, and that is provided in our Google folder for Handout 10. Okay, in Part A, we considered the model and also the hypothesis tests and confidence intervals for the model parameters. Here we're going to talk about the model assumptions. So Part B discusses the assumptions for the model. Okay, in the context of this problem, we can write our statistical model in the following form here. So I'm just putting in PNB for the Y and age here for the X. The mean, again, of this is given by the regression line here. The variability is given by the error term or the residual value. And one additional consideration is that the response needs to follow a normal distribution. So in order for the theory to work out, and in order for those tests and confidence intervals that we considered in Part A to be valid, the distribution of the response should follow a normal distribution. Now, in practice, that requirement is a little bit, we need it for the theory to work out. That is true. But in practice, what we really need is just that distribution to be fairly symmetric. We do not want to be doing regression analyses on distributions that are skewed or on distributions that have extreme outliers. But technically, the theory says that the distribution should be normal. So oftentimes, we will write our regression function in the following way, or with the following setup. We'll say that the response has a normal distribution with the mean given by this quantity and the variance there by that sigma squared, which is a constant variance function. So what does that mean in the context of data? So what that means is that if I want to figure out what the mean is of the distribution of proportion nose black for a line that is 2 years old, what I'm going to do is I'm going to use the line to estimate the mean here. It's given right there. The variability in this distribution is going to be given by my sigma value, or my sigma squared value. So the variance here is sigma squared, but if I write that as the standard deviation, I can just take the square root of that. From my output, this is actually the RMSE value, the root mean square error value. So again, if I want the average percent nose black when a lion is at age 2, what I would do is plug 2 into this equation, and I would get the mean. So here I'm looking at, for age 2, what can I say? Well, the mean is going to be given by beta 0 plus beta 1 times 2, because that's the age there. The standard deviation is just going to be given by sigma, which is just the square root of the variance here, as I said. And from what I have up above, that's going to follow a normal distribution. Now that's assumed, or that's a consideration or an assumption that's made. If I move up to age 5.25, all I need to do is just switch what I plug into the equation. So at 5.25 here, that would be the second one, I can see that my mean is going to shift up to about 0.4 or so, roughly. The standard deviation here is going to be given by sigma squared, which again is the same quantity as age 2, and it's going to have a normal distribution. Or if I jump clear up here to 10.35, the one way up on the right, that's going to have a normal distribution. It's going to have sigma as my standard deviation, and if I want to know what the mean is, I would just plug the mean into that equation. So this is the theoretical consideration. Oops, sorry about that. This is the theoretical consideration for a simple linear regression model. Now, under that specification up above, the following must be true. So these are the assumptions. These first four are the assumptions. Number one, a linear relationship, okay, a linear relationship exists. Okay, so if we're going to use this model right here to determine the mean, then that should be an appropriate model. So the relationship that exists between age and P and B is indeed linear. I mean, that's an assumption I'm making. It's determined by the form of my model, but that is an assumption that I'm making about the relationship between my x and my y. A second consideration is the constant variance that we've talked about. All of these distributions have a constant variance. Okay, so that's another assumption that we're making. The variability in the residuals is the same irregardless of my x value. So no matter where I'm at for the age, the variability in the proportion nose black stays the same for small ages, for medium, and also for high ages. That variability is constant. A third assumption is that I have independence between my observations. So what that means is that the observations, if observations are independent, then one point does not influence another point in our regression model. Here, these are different lions at different ages, so I don't anticipate there to be any problem with the independence assumption. If I am trying to model the unemployment rate, maybe my response is the unemployment rate, and my x-axis is maybe time over the last 2 years, those are not going to be independent of one another. So the unemployment rate that I see in February is influenced by the unemployment rate that I see in January. So there's certainly ebbs and flows to the unemployment rate. One month is dependent on what happened on another month. So in that situation, if you're trying to model time series data, if you're trying to model something like unemployment over time, you're more than likely going to have problems with this independence assumption. There are special regression models that are used for data that is collected over time. Those are called time series models. The last is just the normality assumption. Again, we assume that here, that the response follows a normal distribution. The other is not really an assumption, but we do want to be careful about outliers. So outliers can be problematic in a regression analysis. So we want to make sure and take time to check for outliers. There's an easy way to check for outliers, and that is just to use the empirical rule. The empirical rule states that about 95% of the values should fall within 2 standard deviations of the mean. Well, we are assuming normality. My mean here, my mean residual, or my mean error term is going to be 0. So to check for an outlier, all I need to do is just take 2 and multiply it by my standard deviation. I need to go 2 standard deviations, or 2 sigma values. As I said a moment ago, our estimate for sigma is just the root mean square error term. So I would take my root mean square error from my model, multiply it by 2, and if I have any values that are beyond that, then these would be considered outliers. We'll show you this for the lion data here down below. So how do I verify the assumptions? So here's just some examples of good patterns that I want to see and bad patterns that I don't want to see. So if I'm talking about a linear relationship and I want to verify that assumption, what I want in my residual plot is the following. I want random scatter above and below this horizontal line. I do not want to see trends in this plot. Now, I'm talking about the residual plot here. So these are all done using the residual plots. So I do not want to see a trend in my residual plot. If I see a trend like this, this usually indicates that you are missing an important predictor variable. So something other than age might be causing the lion's nose to be black. If you see something like this in your residual plot, that just means that your linear form is not sufficient. You should probably consider a polynomial. And this particular one that I have here, it looks like a third-degree polynomial might be useful in modeling your response. For the constant variance assumption, again, an ideal plot is just going to have random scatter above and below the plot, of the line, excuse me. If you have either one of these situations, these are bad situations. Both of these are situations in which the variability does not appear constant as a function of x. The independence assumption. If you have positive autocorrelation, then you're going to have this type of pattern. It's kind of a snake pattern or a follow the leader type pattern. These are the types of patterns that you would see if you're modeling unemployment, for example, over time. You also have the other extreme, which is negative autocorrelation, which is extreme bouncing back and forth. This one here is less common, but this is negative autocorrelation. If you have either of these, you should not be using your standard regression model. The normality assumption is just checked by looking at a residual, the normality assumption is checked by just saving out your residuals and making a histogram of those. You can overlay a bell curve on that, or you can just look at the normal quantile plot as I have shown here. This would be an ideal pattern here. Okay, how do we check for the assumptions then using our residual plot? So the residual plot is a plot that is returned when I fit a model. So when I fit my statistical model, maybe I should go through that quickly. Let's do that one more time. When I fit my model, one of the graphs that I'm given is a residual plot. It's this plot here that's about partway down. This residual plot has the predicted on the x-axis and the residuals on the y-axis. So what do I want to see in this plot? I want to see, again, random scatter above and below that horizontal line. So linearity, yep, that looks okay because I don't have any profound patterns in this plot. I don't have like a parabola pattern or anything like that. I have constant variance here. That looks okay. I might have slightly less variability here on the left side, but it ain't too bad. So I'm going to say constant variance is okay. The independence assumption is the snake pattern or extreme bouncing back and forth. I don't have any of that, so my independence assumption is okay as well. The normality assumption, I have the histogram and normal quantile plot down below. So we'll look at that in a minute. And here I'm snapping a line here at 2 times my root mean square error. So my root mean square error for my model, if we go back and look at my root mean square error for my model, it's about 0.12. 0.12. Multiply that by 2, so that's about 0.24. So any points that are outside of that 0.24 or negative 0.24 would be considered outliers. And I indeed have a point that would be considered an outlier. So we should identify that point. It's observation number 18. This particular lion is 6 years old. Its proportion of nose that is black is at 72%, but my model predicted it to be about 45%. So for this particular lion, for some reason, the proportion nose black, their actual proportion is much higher than what I predicted it to be. So my residual here is pretty far off. Again, the residual would just simply be this quantity minus the prediction. So that particular line, we didn't do a very good job of predicting their proportion of nose black. How about the normality assumption? Let me show you how to create this graph. So when I fit my model, from the drop-down menu, I can say Save Columns, Residuals. Okay, so maybe I should say first here, the histogram is not provided in the standard output that you get from the fit model. But I can create it by saying Save Columns, Residuals. That's not going to do anything to my output, but it is going to put the residuals over here in my data table. So now I have this residual column. Now I can just go Analyze Distribution. I want to make a summary of these residuals. Turn that horizontal. There's my histogram. I can put a bell curve over the top of that. So from my drop-down menu, I can say Continuous Fit Normal. That puts a bell curve over it. You can also ask for the normal quantile plot. And that's what I have done here in the notes. So this is what I included in the notes here for you, was the histogram with the normal quantile plot. The histogram here looks pretty good. I mean, it's not perfect. We have some of this is a little bit too high. It should be chopped off and put here. We have a little gap here. But if you look at the normal quantile plot, the points fall pretty well on the line. So I feel pretty comfortable about the normality assumption. So overall, it looks like most of the assumptions are okay. I do have one outlier here that exists, observation number 18. What we do in practice is we could take this observation out and then just refit the model and see how much it changes things. If it doesn't change things very much, then we can just go ahead and leave that lion in our analysis. If it tends to change the model a lot, then you have a decision to be made of whether or not you want to include this particular lion in your model or not. The last plot here is just a plot of the predicted versus the actual. Now this is one of the plots that I get in my model output here. It's this plot right here. So this is the plot of the predicted versus the actual. This plot tends to have, I don't know, a lot going on. It's got this bands going on here. It's got the horizontal line here. What I often do for clients when I'm doing an analysis is just save not only the residuals, but save out the predicted values. So if I go back to my spreadsheet here, now I will have the residuals and the predicted values. And I can just make a scatter plot of the actual values, which is this column here, and my predicted values. I mean, that's what this is right here, is just a scatter plot of the predicted percent nose black against the actual nose black. If your predictions are doing well, they're going to fall real close to this line. If they're not doing very well, they're going to fall off of this line. So right here, for example, is that outlier that I was talking about earlier. It had a proportion of nose black at about 70-some%, but I was predicting it way down here at 45%. So the line here is my prediction. You can see that I was really far off for that particular point. But for the most part, I'm pretty close to the line. If I obtain Pearson's correlation coefficient for this plot, I get a value of about 0.8156. So if I'm looking at the predicted versus the actual, and obtain a Pearson's correlation value off of this plot, that's going to give me an indication of how related the predicted values are to the actual values. This Pearson's correlation is pretty high. In fact, if you take this correlation and square it, you actually get the R squared from the model. So that's another interpretation of the R squared, is that it's just the correlation squared between your predictions and the actual outcomes. If this correlation is really, really high, close to 1, then all these points are going to be really close to the line, and I'm going to have a really high R squared. If the predictions are not related to the proportion black, Okay, if their points are kind of just all over the place, then Pearson's correlation value is going to be low, and I'm going to end up with a low R-squared in my model. Okay, that does it then for the model assumptions for a simple linear regression model. Thank you.